Previously, we looked at the exponential growth model for a population P. The constant K represents a reproduction parameter. In this model, the population growth continues unabated. Although such a model may be accurate during the early stages of growth, as time goes on, other factors, such as the food supply, will begin to affect the real growth of the population. A better description of population growth is given by the logistic equation, which includes an inhibiting factor P over K. So, suppose the value of P is much smaller than the constant K. How does the logistic growth model compare to the exponential growth model in this case? Click the Submit button after selecting your answer. If the population starts out at a value much less than K, the beginning of logistic growth is similar to exponential growth. Now, let's look at the slope field for a logistic differential equation. A particular solution curve corresponding to a given initial population is shown on the slope field. Move the slider to change the initial population value. The value of P over K is shown for each curve. What does the constant K appear to be? Click the Submit button after selecting your answer. The constant K is known as the carrying capacity. It is the maximum population an environment can sustain in the long term. Notice that if the population starts out less than the carrying capacity, the population increases at first and then levels off at the carrying capacity. If the population starts out greater than the carrying capacity, the population decreases at first and then levels off at the carrying capacity. If the population is initially equal to the carrying capacity, what happens to the population over time? Click the Submit button after selecting your answer. If the initial population is equal to the carrying capacity, then the rate of change of the population is 0. Therefore, the population remains constant over time. The logistic equation is separable, so we can rearrange the differentials. To solve the equation, we take the integral of both sides. The solution of the integral on the right-hand side is trivial. The integral on the left-hand side can be solved using the method of partial fractions. What is the solution of the integral on the left-hand side? Click the Submit button after selecting your answer. After determining the general solution, we can impose the initial condition that the population is P sub 0 at time t equals 0. We then are able to express the population P in terms of P sub 0. We see that as the time approaches infinity, the population P approaches the carrying capacity K. Now, consider this logistic equation that describes the growth of a certain population of animals. The initial population of the animals is 200. What is the population size at time t equals 40? Click the Submit button after selecting your answer. Making a graph of our results, we can see how close the animal population is to its carrying capacity at the given time. There are other potential uses of the logistic model besides population growth. The spread of a contagious disease is one. Suppose there is an island with a total population equal to T. One person has a contagious disease. That person comes in contact with other people who then contract the disease. Those people contact others, further spreading the disease. An epidemic has started. Although the spread of the disease may initially seem exponential, it cannot remain that way as the number of infected persons approaches the total population. We can use a logistic model, such as that given here, to study the spread of the disease. We see that the rate of infection is proportional to the product of the number of infected persons and the number of non-infected persons. What is the solution to this logistic equation? Click the Submit button after selecting your answer. We assume that only one person is infected initially. We then can derive an equation for the number of people infected at some time t. Suppose we know the values of the total population and the number of infected persons at a given time. What is the value of the constant k? Click the Submit button after selecting your answer. After determining the value of k, we can make a graph of the solution in order to see how the disease spreads over time. Now, suppose we wish to study the spread of a rumor. We can use a logistic equation to model the spread of a rumor. One model states that the rate of the spread of the rumor is proportional to the product of the fraction of the population who have not heard and the fraction who have heard it. Assume the total population is given by T, and the fraction of the population who have heard the rumor is given by Z. Which of the following is a differential equation that is satisfied by Z? Click the Submit button after selecting your answer. After determining the proper logistic differential equation, we need to solve it. Which of the following is the general solution of this differential equation? Click the Submit button after selecting your answer. Suppose we know the total number of people in a certain region. We also know the number of people that have heard the rumor at a given time. Furthermore, we know that 1/4 of the people in the region have heard the rumor by a certain time. At what time has half of the people heard the rumor? Click the Submit button after selecting your answer. We can make a graph of our particular solution to see how the rumor progresses through the population with time.